Okay, I dare to start already, even if some people are still coming in. The reason for that is that I have to get to Vienna, and that seems to be a bit complicated today. And I was given choices, and all the choices were preponing my travel, not postponing my travel. So I have to run away at 1 o'clock sharp, otherwise I'll not get to Vienna today. That's unfortunate, so I have to speak a bit faster, and I should also start in time. That's why I, even if not everybody is here already, give it a shot right now. So welcome to this blog on snow hydrology, and I particular view at remote sensing from the perspective of snow hydrological modeling and monitoring of snow water resources. So I take a little bit of a top view approach, high flight level, and discuss with you how you can make use of those snow remote sensing products, in essence, to assess available snow water resources, snow melt runoff, and anything that's connecting between the cryosphere and runoff or hydrology in the end. So this is the content of today's blog on snow hydrology. I want to give you some background, some introductory remarks, and then we shall discuss a couple of modeling strategies for snow water blend and snow melt runoff. And then we go through individual remote sensing products and supporting data sources. And again, I'm taking the perspective of a model, and I will discuss with you how I see those data if I was a model or if I was tasked to run a model with this data. And then we can discuss a little bit about how to integrate those observational data into snow models by way of assimilation, data assimilation, other things. And I may have some time in the end to also show you one real-world application of all that, if time permits in the end. Okay, feel free to interrupt me if you have, let's say, important questions, and otherwise, if I just run away, I'm not wanting to be impolite, but feel free to send me any question by email or other sources of contact if you run into questions that we can solve here on spot, because we are limited in time. So I'm not biting. You can write me emails. It may take a few days before I respond, but feel free to ask any questions then after the fact today. Okay, let's start with some introductory remarks and some background information. So operational snow modeling and monitoring has relevance for a lot of disciplines, and I just summarized a couple of our customers of snow products from our Snow and Avalanche Research Center, and as you can see, the variety is from, just recreationalist all the way to natural hazard mitigation, hydrology, hydropower being obvious ones, but we also send those products to people who do avalanche warning or doing just, sheer basic research. And most of all those people who use those snow hydrological data products, they see remote sensing an interesting data source, but they're not really helped with that alone, because it just contains, let's say, has information with gaps, and it's not to the point where they need it, because at the end of the day, they probably need snow water blend or snow melt or something like this, and there's not the single remote sensing product that helps them alone. Exceptions exist, of course. And a combination between model and data assimilation can typically mitigate most of those problems, because in the end, if you see model data assimilation combination as something that can provide you with a product that has all variables you're interested in, doesn't have gaps neither in space nor in times, because it's a complete model in space and in time, you can just see this as some box that basically complements the data that you observe. You can't observe everything every time at every location. It's just not possible, and can add additional parameter, can add locations where you can see, let's say, within a forest, you may not be able to see that from optical remote sensing, because you just see the canopy, not one underneath. A model can help, for instance. Or you may have clouds and you don't see the snow under the clouds. A model can help you with that. So see this as something that can complete your data set in multiple aspects, in the temporal dimension, the spatial dimension, and the variable parameter space, and so on and so forth. So, obviously, model of snow and snow hydrology comes with lots of challenges. And here are a couple of arguments to be put in place. So obviously, forcing data at relevant scales is a big issue. And what I mean with relevant scales is if you want to run a model at, let's say, 100-meter resolution, and for that, let's say you run a physically based model, and you want to run redistribution modeling of snow, then you need wind fields. But who's giving you 100-meter resolution wind fields over the entire Alps? That just doesn't exist anywhere. So you need to create this field yourself. So basically, models are great, but you need to also be able to provide it with relevant forcings, and I mean at the relevant scale. So if you want to resolve something at 5 meters, you better have something to provide you with a forcing that provide the variability that's relevant at these 5-meter resolution. Also, the representativeness of the observations, be it the remote sensing data to be assimilated or validation data sets, need to be ensured. And, well, to make a bold statement, most monitoring data, they are from flat, open sites. They are not in the mountains. They are not in steep terrain. They are not in forests. And if you're interested in that stuff, your monitoring data typically is not representative of what you're interested in. So that's often a problem. Also, obviously, there's a very complex spatial temporal variability in everything related to snow. All processes have this great spatial temporal variability. Just look at this image of the forest. You know, you can probe in the forest and you get everything from 2 meters to 20 centimeters, and that's just next to one another. You have a hole here, you have a buried tree, a trunk, something. So, you know, it's all over the place. And as I said, it varies within meters. I wouldn't be surprised if actually one of the person is in the audience here. That's on the picture. Not guaranteed. And then obviously expectations, you know. You go to SLF, you want snow data set, and it better be perfect at the meter where you get a feedback, because people will, you know, run around, make a message on Facebook, the SLF snow model sucks because I'm here. Yeah, that's a problem, and that's a problem which I'm faced with quite often, if you can imagine. Let's talk about spatial and temporal variability of snow. I think from the perspective of a model, there's two things that are important to understand. That's the scale dependency of those variabilities. And what you can see here is relative snow maps for every March 15 since 40 years. You get a clip out of 20 years. And you see patterns where you have more and less snow than the average long-term mean. Anything in red is less snow, anything blue is more snow than the average long-term mean for March 15. So you can imagine what this data means. And you can see that the patterns are super variable, every year different. In some cases, you have patterns where you have more snow on the northern face of the Alps and less on the southern face of the Alps, or the reverse patterns. So if you see 1972 and 1973 as example, you have everything blue, you have everything red. And, you know, they just are all over the place, and they won't tell you in advance the next year will be a blue year, the next year will be a red year. It's just bound by weather, and weather is variable, obviously. So what I'm saying is that between years at large scale, you have a strong variability. Now let's go on the other end of the spatial scales and look at 2 consecutive years at very small scales. So these are images from a remote time-lapse camera, and they were taken on a similar date in 2 years, and you see that those patterns are almost identical. And the reason for that is that the processes that lead to some areas having later snowmelt than others is bound by microtopography, and the microtopography doesn't change as weather does from year to year. So you have a change in between year variability at different scales. And if you put this together, you get something like this, where you have the spatial scale from large to small, and you have different effects that affect the variability, starting in large scale with elevation dependency of precipitation phase, going to weather aspect, slope, going to microtopography, and along this gradient of different effects of these aspects to snow, you see that the interannual variability moves from strong to weak. So weak interannual variability means there is less difference between year-to-year differences as opposed to strong interannual variability. And there's some sort of a arbitrary scale break from the modeling perspective where you say, okay, anything left of this bar is what I resolve in my model, and everything right of the bar is what I treat as subgrid variability, unresolved, treated statistically. And where you put this bar is absolutely up to the modeler. So you can do what you want. You can shift the bar all the way to the right, or you don't use a model and shift it all to the left. So if the break is here, you're probably talking about a physically based model that can resolve, aspect dependence, melts and stuff like that, slope dependence, snow redistribution stuff. And if you go back, that's probably where a temperature index model would be located on this chart. So what I'm saying is that this aspect of scale dependency or variability has implication of the type of model that you should use for a given purpose. And the given purpose is defined, do I want to see differences in snowmelt between south and north facing, or do I not care because I just need bulk figures of East Switzerland, West Switzerland, I don't care about this level, depending on which I set the bar to what my requirements for modeling are. So this has an implication for the model choice. Second thing is the temporal variability. Also, this has implication for stuff we discuss later on in this lecture. And I would give you an outline of the concept of 3 different periods during the build-up and the depletion of a snowpack. And I visualize that by way of looking at a snow depth record over the course of an entire season, where the vertical axis is basically the snow height, and the color is reflecting one internal snowpack parameter. In this case, we are looking at snow temperature. So basically just read one vertical line as a temperature profile you take on a given date, depending on where you're on the x-axis. So if you take a general profile, you will see it's cold on the top 20 centimeter, it's somewhere intermediate, and you have isothermal 0-degree condition for the lower half of the snowpack. So already here you see that there is maybe 2 blocks. They're denoted like blue, and then you have red and green, somewhat similar, and you see that at a certain given time you will see that all of a sudden the snowpack turns very quickly into an isothermal state where everything is 0 degree and you're done for the rest of the season. So from the temperature perspective, you have those 2 blocks with some transition. So it's colder and night, you basically cool up the snowpack to very cold temperature if you have clear sky nights in December, January, and that just doesn't happen anymore in March, April. That's something you can observe. Now, if you look at the same thing from the perspective of snow density, you will see all sorts of more structure that you weren't able to see in the temperature, like those ice lenses or layers, crusts, stuff that's being buried. You have a new snowfall, you have, let's say, surface hoar, or let's say a formation of an ice layer, and then it gets buried, it gets basically compacted by way of settling of the snowpack, and you see how these features survive over the course of a season. No question, you probably have dug snow pits or have seen images of that, and you see that there are fine layers, and that's what you see here. And now you see this characteristic bump, and that basically defines the definition or the distinction between the green and the red bar. At some point you see that this bump starts here, which gives the beginning of that, and then when this is all the way down here, you basically have the transition to the red phase. And at the beginning you have a density increase that's somewhat slowly, subtly settling the snowpack, and then you see an acceleration by some sort of processes where all of a sudden the snowpack gets darker, like a jump change, and at some point you have this high density all the way through to the bottom of the snowpack. With some, there's some issues here where you have some new snowfall, but basically that's all driven by the presence of liquid water. And at some point you just get liquid water percolating down into the snowpack. That may take a week or 2 weeks or 4 weeks, such as in this example. And at some point you're just all the way down. And that's basically the ripening phase where you turn a dry, cold snowpack into a ripe, saturated isothermal snowpack. So the green phase is basically the ripening and the transition phase. And that has implication for modeling and for the relationship between observations and the model, as you will see later. And then, yeah, the solution, that's liquid water content, and as you have guessed right, you see that those density imprints that you saw are basically effectively due to liquid water presence. So obviously you have some warm spell here, it leads, or maybe even rain on snow, and it leads to some first percolation, but then it turns cold again and you see nothing like that. It gets buried, it sinks a little bit, and then you have another finger of percolation, another, and at some point it's so much liquid water that you make it all the way down, and that's when you start the begin of the snowmelt runoff. Only if the water makes it all the way to the bottom of the snowpack, you can have snowmelt runoff, obviously. So see this green phase as the ripening and transition from fully dry, cold to fully saturated isothermal 0-degree snowpack. Well, that has some implications. Once again, an example here. This is a twin station data assimilation experiment. This is basically two snow stations in the same location, more or less. They're just a few hundred, not even hundreds, few dozen meters away. They should see the exact same snow observation in terms of snow depth, the black points, but they didn't. For some reason, one did show something and the other showed some incredible decline in snowpack. For some reason, most likely wind-driven, shoveling, whatever, some manipulation. And then you see various model simulation given the same weather input, because they are so close to one another that we didn't assume that there was any different weather between those two stations to drive the snowpack, excluding terrain shading and all this type of stuff. And what you can see that in one example you were able with data assimilation to nail that pretty much down to the observation, and the other, the model just refused to meet those observations. And the reason is the model is a physically based model, and if you tell it, please now deplete 50 centimeters of snow, and the snow is cold, there's not enough energy, there's no way you can force this model. And in a data assimilation situation, you must acknowledge the fact that even if you want to remove 20 centimeters without violating physics, in some situations it's physically implausible, and then the model just can't do it. And that is an important aspect of data assimilation. You change something and the model doesn't react. And this is a perfect case where some observations were just not plausible, and gladly, and that's a good setup of a model, the model refused to do something that it thought was implausible, and obviously did something correct in this particular situation. So be aware that physically based model cannot be manipulated excessively if the physics doesn't allow these things to happen. So an avalanche, if it's not represented in a model, you cannot remove a meter of snow within 10 seconds. That's physically implausible if the process of avalanching is not represented in the model, and the model will just not do it. Okay, now let's talk about modeling strategies. And I'm first talking about forward modeling. Basically, you are in September, you initialize your model, and then as the time progresses, you continuously, sequentially advance your model. And you don't have the possibility to go back by 2 months or something like this, because who cares about snowmelt forecast from 2 months ago? You wanted to have it today for the next couple of days. So think about forward modeling as something where you're most interested in the next couple of days. Most of these models are somewhat set up like this. And I'm talking just about distributed model, not model that just run at stations, because we're talking about hydrology, remote sensing. That's all spatially explicit information. So you have some sort of input data. They can come from numerical weather prediction, reanalysis data set, even interpolated meteorological station data is being used, regional climate model, all sorts of things. And they typically run at resolutions of kilometer, 10 kilometer, 0.25 degree, something fairly coarse. Whereas snow varies, as we discussed before, at the meter scale, 50 meter scale, 100 meter scale. So we probably need to close the scale gap between the metadata and the resolution at which I want to run the model. And what do I need for that? Downscaling, post-processing, debiasing, obviously weather forecast is also flawed. Just look at the app and see what the weather forecast says for tomorrow, and then check again tomorrow, and you'll see, oh, that's not perfect. And these are things that can be accounted for in these post-processing debiasing issues. You can do this with physically based dynamical downscaling methods or with statistical downscaling, depending on what you actually need. Then you have observations. They can be station observation, remote sensing observation. You have model output. You can match them up and find, okay, there are discrepancies. And then data assimilation can take over and navigate between the most likely state if the observation and model are having conflicting information. Then the data assimilation's job is, so to speak, to find the best estimate which takes the most plausible information from both worlds, from the model and from the observation. So think of this slide we saw this morning of a rice field where all of a sudden it said, oh, there's 20 centimeters of snow, and it was just water. Then probably the model says, no way, it's not going to snowing right here. And so basically it's plausible that you omit this observation even though it seems plausible because the model says so, and you put more credibility in the model in June 1st or something like this in the mid of Schleswig-Holstein. It's not going to happen. So basically then you will basically select wisely what you trust more. And it's not me saying I don't think that. The data assimilation must do this autonomously without you interfering with that. And that's always the challenge, to train a data assimilation or set it up in a way that it does the right choices in most of the situation, even if nothing is perfect, of course. Okay, I would guess that most forward model in the operational world, which do forward modeling, are somewhat set up like this. Different data sets, different debiasing structure, certain models, some just care about open terrain, Greenland, whatever, maybe there are not so many trees, other dedicatedly model at 1 meter resolution forest snow, so yeah, they can be very different. Some use temperature index model, urban, whatever. So that can be all sorts of model. Conceptual models, like temperature index models, they work in principle because temperature is a good proxy for almost every component in the energy balance, with one exception, which is latent heat. That's not correlated to temperature, actually. And so this is also the reason why in a situation like depicted here, temperature index model didn't predict any snowmelt runoff. It was a rain or snow situation, and the main cause or the main energy contribution to this snowmelt event was by way of condensating relatively hot, humid air. Relatively hot means anything warmer than 0 degrees is hot from the perspective of snow, because snow cannot be above 0 degrees. So if it's raining, obviously it's already above 0 degrees, and so you have lots of humid, warm air that condensates on the snow surface, and if you have very windy conditions, that cause a lot of heat to be released because of the phase transition when you condensate, and that basically leads to an enormous amount of energy available to melt snow in such rain or snow situation because of latent heat, and latent heat just doesn't relate to temperature, and temperature index model just doesn't see the cause for the melt to happen, and it's completely blind to that event. So there are situations where you just don't want to use conceptual model because the concepts don't work, or you use them in extreme condition that these models were never calibrated and trained for, so you have no point. But in general, they work quite reliable if you have larger integrated scales, and if you avoid those more specific situations such as rain or snow or other extreme events. Aspect-dependent melt obviously is not included because you will have the same temperature on both sides of a valley, but you don't see that there's more radiation input here versus this side. So a temperature index will probably model the same snow on both sides of the valley. If you're interested in that, you probably have the wrong model approach here. So that's not a surprise, I would guess. And then, you can get energy balance model to work exceptionally well if you have, as I pointed out, accurate input data. But be aware, and that's something that may or may not come to a surprise for you, also physically based model have lots of parameters that need to be tuned. So if you think like, yeah, that's physics, that's just easy transferable, it just works out of the box. No, it doesn't. A temperature index model has, I don't know, 10 parameters. You can put them together, it will work for the next 20 years. a physically based model may have 100 parameters, and each of them needs some user input. So don't think of a physically based model to be something that works out of a box. It just doesn't. But if you do your homework and you do wise choices and you basically also tune those parameters based on physical observation, which is possible because most of the parameters have some physical meaning behind them, so you know what is a reasonable range for given parameters, you can get to a performance where you see basically the observation disappear behind the model simulation. So the black line that you can see is the observation because it's over plotted by models that are so accurate that you can't even see the observations anymore. And this is a operational model for last year of Switzerland in 5 different elevation bands. So yeah, you know, there's one exception here, so we failed on that. So yeah, they can write a Facebook message now and tell me that our model screwed up. But that's what you can get with energy balance model. If you tune them well, and if you have the capabilities of downscaling the data to the needs of the model. Yes. But if you go in the details and you do a spatially explicit validation, leaving the comfort zone of going to flat field sites in the open that behave nicely because they're in slope terrain, they're in a forest, stuff like that, then you'll realize that a model that looked perfect on the previous slide may actually have some issues, and that's where remote sensing data comes in handy, because they can probably better tell you what the truth is from a spatially explicit or spatially distributed perspective. And here is an example of the same model we have seen before with one component switched on and one component switched off. On the left-hand side, you just see the out-of-the-box model with no lateral redistribution of snow because of avalanching and because of wind redistribution. And in the center, you see the exact same model with this component being switched on. So basically, you have an exchange of snow between horizontally neighboring grid cell by way of wind redistribution and avalanching. And all of a sudden, the same model turns into something that's pretty comparable to a laser scan observation of the exact same mountain range. Both is, I think, at 100-meter resolution over a 42 square kilometer catchment not so far away from Davos. So be aware that a model that looks great from a station perspective may actually look like this if you compare it to something like that. And then you would probably, maybe the model is not as great as it could be. And then it's just a matter of what processes do you want to be represented as a model, and do you have the model capable of doing these process representation accurately enough. So horizontal redistribution is something that's pretty important if you look at a high spatial resolution at those models. Be aware of that, and that's a pretty difficult situation because, as I already mentioned, 50-meter wind fields over alpine topography require some compute power in order to generate those. That's not as simple as it may be. So you don't use your PlayStation for that. You need a serious computer for these type of simulations. Okay, backward modeling, just to give you a little bit of a background about a very classical case of where you can one-to-one apply remote sensing data. And that's a case that's been put on the table, I think, in the 2006 or 7 has seen first applications of that, if I recall correctly. So we saw this here is 10 random stations at the same elevation distributed throughout Switzerland. So I think they are somewhere 2,500 meter level above sea level, 2,000 meter, 500 meter above sea level, and they are from all parts of Switzerland. Same elevation. And you can see that the distribution of snow depths is quite variable between those stations, although they are all the same elevation. And you see that the accumulation rate is different because of more or less snowfall in West and East Switzerland or wherever. And then you have some sort of melt, and you come to a melt out date for those stations, which will rise by, well, a good 5 or 6 weeks. So the range is pretty significant. And the idea of backward reconstruction of snow is, well, I can observe the melt-out date quite accurately. I just need fractional snow cover product and just have a look and see when does a white pixel turn black. and I note that very date, and if I don't have that information because of clouds, I may do some gap interpolation, but at the end I come up with the spatially explicit information of the melt-out date. And so if you believe that modeling the melt-out speed or the melt rate is more accurate than modeling the accumulation with all the unknowns and precipitation forcings, then you can just wait until the season is complete, take the observation, and basically substitute every pixel as one of those dates here, and just run the model backwards and stop the model simulation once you reach that line, when you know, okay, from that point onward, there is no more sustainable backward build up because it's been too cold, and there is no assumption that there's further energy support to do any more negative backward melting. So basically backwards calculating the available SWE at top of winter. That's the main principle, and you're basically running this ramp of this. These are the three phases that we said: accumulation, ripening, melt phase. And you just basically ramp up from here to here, where you know the exact timing of that lower edge of this triangle, and that's basically the principle. And it's very good if you're interested in spatially distributed high resolution SWE and you're not so much interested in let's say, why did that happen? Because this type of approach doesn't give you reasons. Is that precipitation driven? Is that because you have interim melt events in the accumulation? So it's basically not really process oriented. So that's a classic SWE reconstruction using one-to-one information based out of a time series of fractional snow cover based map from satellite remote sensing or other means of remote sensing. Okay, so I'll skip over this slide, that's not so important. And so we already discussed model choices, and to put this all in one slide, you have different arguments. Let's say if we use this triangle, you have process-based models here, you have conceptual models there, and you have near real-time. So basically anything that's not urgent and not pending goes further down. Anything that's operationally near real-time where you're interested in the next hour is as much up as possible. And then you see all sorts of different applications, and depending on which, you will choose a different model. So let's take the case of a SWE reconstruction, which you just had. SWE reconstruction is not really something you do 5 years in advance. Normally you want to do this from a seasonal perspective, doing that in June, revisiting the past year. And it doesn't really matter whether you use a process based on conceptual model, because this choice largely depends on whether you have a large catchment, then you're more on the right-hand side, or a small catchment, then you're more on the left-hand side of things. If you want to do snow research, obviously my recommendation is to use physically based models, whereas often hydrological research, and I don't intend to be mean, it's more like an observation that they often use very long data sets, and please can you give me SWE for the last 60 years, and all I can give them is conceptual modeling, because I can run a physically based model over 60 years. So even if I was asked to provide them with snow data for hydrological research, I would probably tend to go as right as necessary to suit the need of long time series of data. If I'm just interested in the last 2 or 3 years, I'm happily living somewhere down here on the left. So yeah, you can see model choices have different arguments, and you can see if you have an application in mind for your dissertation or whatever, you will probably find somewhere your sweet spot and say, that's me, and then you take your model choices. And then you can maybe send me an email and ask me, what do you think? So that's how things work. Okay, I skipped this discussion because I just basically have that discussion more moderated. So I give you feedback already without asking you for your opinion. Sorry if I don't ask you for your opinion at that point. But in the interest of time, I better go that way. So, supporting data sources. And here I really want to talk you through various data sets taking the perspective of a model. So let's first talk about snow station data. You think, well, that's not spatially distributed. Well, it is, but it has lots of gaps, because between stations there's no information. But even in this situation, station data can constrain fully distributed model. And here's an example. That's stations, these are those circles, the background is the model, and if they match up quite well, you barely see the circles because they have the same color as the background. Unlike in the left situation, and this is a situation where we try to estimate solid precipitation for a particular storm event, and we were wrong at the beginning because the first guess was flawed in that it would overestimate the snowfall limit. So what we needed to do is correct the temperature on the fly with data assimilation to bring the snowfall further down the valley, and finally that resulted in that pattern over here. It's just based on 400 stations. It's not like a fully gridded solution, but you could achieve a fairly good match. So this approach is good if you're interested in regional bias correction, where you have there's a little bit too much in the west, a little bit too little in the east, and maybe a little bit uphill and not so much downhill. So these type of regional patterns, they're well suited if you just have those, let's say, generalized pattern that you try to debias. So it's powerful in removing those large-scale bias, but it's definitely not suitable if you have this one station that sticks out, or if you have a very narrow föhn valley that removes snow in no time. That's something where your station will probably be in the wrong location, or it's in the right location, and the data assimilation say, you're just one station, I don't believe you. So basically, most likely it will not fit the case. But then comes assimilation of snow depths and snow water current products. The cool thing here is they're typically pretty much on top of what the model is supposed to do. Calculate SWE or calculate snow depths. So basically there's no gap between what you observe and what you're interested in. It's the same thing. So it's pretty straightforward from an assimilation point of view. If you have the information, okay, here's my model, and oh, here's an observation, then you pretty much have a good information what you're supposed to do. You will somehow make some choices how you remove the snow depths from the simulation, but you have multiple options. And the good thing, if this information comes in every now and then, let's say every week or so, you can make very informed choice what you need to do in order to make your model replicate or approximate those data. So it's fairly straightforward. This here, in fact, is a remote sensing product, but not from spaceborne. It's airborne, laser scanned data at fairly high resolution. The only thing in order to make that a SWE map is that you need to run a complementary snow density model to multiply the scanned snow depths times density to get a SWE product. That's something that's fairly operational in Western United States. You probably have heard about the Airborne Snow Observatory. They provide these data on a weekly or bi-weekly schedule for large areas in Western United States. So just Google ASO if you're interested in this type of stuff, and they provide that to the water managers there. If you have such data, great. I'll take it any second and assimilate that in my model, and I'm happy because there's nothing that's more suitable than doing something like that. Only problem is that these data often look super trustworthy, and if, let's say, take the example of the rice field that's supposed to be snow from the observation point, the problem is that it doesn't say, oh, here's this isolated single station which I just neglect because I don't trust the station. It provides every 5 meters the information, here's snow, here's snow, here's snow. And so the sheer number of information telling you the wrong thing at some point makes it more credible. And that's then a problematic situation. Measuring snow depths is fairly straightforward, and at some point you trust the data and then you ruin your model because it misinterpreted something stupid. So that's the only danger I see with these type of products. Now, snow cover fraction, something that I'm pretty sure you have seen extensively in the last couple of days. You may think, well, it's nothing more simple to assimilate snow cover fraction in a model, but in my opinion, there's little potential to do that. And I'm now, as I said, taking the perspective of the model. The problem is that the information about, oh, now you should be snow-free, comes at a time where the model has done its job already. And in a forward modeling procedure, it just comes at the end of the season, where I need to fix the model somewhere at the beginning of the season, maybe. So if I have an issue with a snowfall in December, which I did not get because the input data was not right, and I hear about this in April, then what do? The season is over. So this again, just from the potential of forward model, little use of that data. It's great for reconstruction, it's great for reanalysis, it's great for everything in retrospective, but in a forward modeling situation, the information is just coming too late in the season. So it's also better in low resolution applications. So you may wonder, why is that? But the reason for that is if you have low resolution applications, then you have not the situation where, from a perspective of a 1 meter grid cell, snow cover fraction is probably 100%, 100%, and then all of a sudden the snow is gone and you have 0%. The larger the units in which you model are, the more you have a smooth transition from 100% to 0%. And it may give you 1-2 months of time where this information is useful. Because if you're already here in March, okay, we start to have partial melt out, and it progresses into May, then I have information between May and March which I can use. So the larger the units are, the more likely there's at least some time to make use of that information. That's why it seems counterintuitive, but from, again, model perspective, the larger the units are, the more useful I think they are because of the timing at the end, or not so much at the end of the season where I see something in that product. Okay, and finally, very obviously, knowing there is snow in a remote sensing pixel and the model doesn't have snow anymore, doesn't tell me anything about what I'm supposed to do. How do I add the snow? Is that this much snow, 2 meters of snow? I have no clue. It's just telling me it should be white. And it doesn't give me any information beyond that, so I can't use that information. Just that, okay, I screwed up, but I don't know why, when, how much, is that just a centimeter or not? So that's also not very useful. So again, taking this perspective, I think that's not the most useful data. Okay, now let's go to wet snow products. The situation is different because knowing the timing of the transition between phase 1 and phase 2, that's pretty impressively interesting, because it tells you, okay, now your model should start to move on and get the snowpack wet and eventually turn the snowpack into a saturated isothermal snowpack. So you get information at an interesting time of the year. And if your model is not in that state already, where you start seeing liquid water content, then you better get your butt in gear in order to ensure that the model does reflect what you see in the observations. And so that's an interesting time to get that information. And this is why there's quite a potential in assimilating that into a model. So it comes at the right time. You may need some spatial aggregation, because you may just see a little bit of wet snow here and there because of a sun ray hitting a stone, and the stone, is super sensitive to even very small amounts of liquid water content. You may not want to immediately turn your model into a melting state just because there's a hot stone somewhere out in the snowpack. So that's why I advise to have a little bit of spatial aggregation to filter out those hot pixels and those individual issues for very high resolution data. It's best in tandem with microstructure resolving model, because basically you see liquid water content in the top 1, 2, 3 centimeter already, and better your model can resolve that as well, because otherwise, if you have a bulk model, you will not have liquid water content if there's in fact just a centimeter of wet snow on top of the snowpack. So to close the gap between the sensitivity of the remote sensing product and the model, you better have a fine vertical resolution in the model. So that's also a negative point, that the retrievals saturate a little bit too quickly for making it easy to compare the states in the model and the observation. And obviously, yeah, there's a large gap between the first occurrence of wet snow and the onset of snowmelt runoff. So please don't mistake wet snow maps as snowmelt runoff maps. That's absolutely not the same thing. Just once again to put out a warning finger here. Okay, assimilation of snow albedo products. This is also an astonishingly difficult case for data assimilation, even if you can basically just copy that into the model, because it's on top of the snowpack. And if you say, hey, my snow surface albedo is now 80%, it was 90% yesterday, that's not violating any physics, because it can happen. You just need a Sahara dust storm, and it can switch from 90 to 70% in no time. is physically plausible, and you will not destroy any model physics because it can happen in nature as well. So direct insertion is at least something that's physically viable and plausible in such a... So it's technically very simple. The problem is what you see in this example. And here we just ran, just a few days ago, some example of assimilating information about albedo, in particular fresh snow albedo. And you see the fresh snow albedo is set in the model at those instances where you have some significant snowstorms somewhere in December and January. And then you see that feeding it with a spread of a range and new snow albedo parameterization perturbed by a range of 85% of the a priori guess to 115%, so a large spread, you don't see anything. It just doesn't react. No reaction. You put a different value and the snow model just continues to do what it used to do before this perturbation. And then magically, 3 months later, you see, boom, the model just disappears. And the value you put in here all of a sudden has a large impact just 3 months later. And the reason is that this new snow albedo basically is determining how much energy the snowpack takes every single hour during the day. And it will just cause that the ripening, or the point where the snow becomes isothermal, just is a little bit faster or a little bit slower, and it can actually make a difference between it's starting April and it's starting June. But you just don't see anything of that because only the transition from dry isothermal to liquid water content is then making an effect on the snow depths because of the advanced compaction with presence of liquid water content. So the problem is you perturb a parameter and you don't see any effect. And you have to wait 3 months until you see an effect of what you did way, way earlier. And that's a very difficult situation for a data assimilation that's sequential. If you don't care and you just run one simulation over the entire season, that's no problem. But if you need this information and you want to do something and also validate if that what you did was good or bad, we'll see no response. And that makes it technically complicated for data assimilation. The other issue being that snow albedo is not just one number, it has spectral, it has director characteristics. I assume that's all covered in the last couple of days. So nothing to discuss here again. Okay, and then finally, snow surface temperature or land surface temperature. It's a good parameter because it's a kind of sanity check for all physically based model. If the land surface model is completely nuts in your model, you're probably doing something else wrong, because it's basically the outcome of the closure of the energy balance. So if your model says, oh, minus 30 degree, and in fact it's at 0 degree or minus 10 degree, then you should probably fix your model some other place. So it's a good sanity check. On the other hand, it's not so ideal because these data often contains other things, in particular larger or coarser scale. So if you have rocks, trees, water beds, you get an information that you interpret as snow surface temperature. And in fact, it's just a mixture of different surface temperatures. So unmixing snow surface from land surface is not so easy unless you have confidence that this is really snow surface temperature. It's not the ideal. It's again, a bit counterintuitive, but it's best at super high spatial and temporal resolution because it arrives at high temporal and spatial resolution. As you can see here, the shadow of a tree moves. You can instantly see the effect of the same high spatial resolution in the land surface or the snow surface temperature. And as your model resolves that, then this is super interesting information. If your model is not at that resolution, you probably don't want to use this integrated information. And just one more thing, if you look at a large snow surface somewhere out in the mountains and you take a video of that with a thermal infrared camera and then you see a wind gust coming in, you will see the chill of the wind gust of, let's say, 3, 4, 5 degree. For as long as the wind gust is coming through, you actually see waves. And if you just take a snapshot of that, say, oh, it's minus 15 degree, it may just be a little wind gust coming through. So the information is so temporal variable that it's hard to just take one information, one snap, and shut on time and not integrate them over time. That's then becoming very complicated. Okay, just a few more words on integration of the data. So a little bit on data assimilation concept before I have to run away. But I'm pretty much at the point where I wanted you to take. I think this last section was pretty important for me, that you understand how I see that if I take the model data assimilation perspective. So here comes the concept of a perfect model assumption, which is a very convenient solution. The perfect model assumption basically says, okay, I have a model and it does whatever it does. And there's a couple of screws. The one screws is the forcing data and the other screws are model parameters. But there's nothing wrong with the model apart from not knowing the exact parameters. So I trust that the model is set up and has the right physics in it. The only thing I don't know is roughness, length, I don't know, transfer coefficient here and there, all those parameters. These are basically guesses. And these can be tuned, and the assumption here is if I just know the perfect parameter space and I have the perfect input data, the model provides the absolute perfect outcome. That's the assumption. It's not so far from this assumption as you've seen previously, where you can get the model to nail situation quite well, but it's obviously not as simple. So the data assimilation job becomes the job of estimating the model parameters and the forcing corrections on the fly. That's what a data assimilation procedure under the perfect model assumption does. The good thing about this is never violates any physics, because you're not changing the model, you're just changing model parameters within their boundaries of physically constraints, obviously. So you, by definition, ensure that you never get unphysical states in the model. And it's absolutely independent of what type of model you use, because if you can break the model, then you can also apply that for any sort of model. It can be microphysics model, it can be nonlinear, complex, multi-layer, everything. Nonlinear, no problem, because you basically just use the model as is, and the only thing you change is model parameters, and so you can't break anything. It's basically a safe environment from the perspective of the model. However, this is typically something you do at the station information, or where you have information. It doesn't help you much if you have grid cells where you have no observation. Think of, okay, forest tile. Think of, I don't have observation for other reasons, because there's clouds, there's whatsoever. Steep cliff, I can see it, you know, overlay, whatever. And then things become complicated, because generically this doesn't offer any solution to inherit information from these two pixels to a pixel where you have no information. So you have to fiddle out something how you can solve that problem. When you can manipulate the states of a model, so here you do not manipulate the model states, you perturb model parameters, whereas here you adapt the model outcome, not the model parameters. But if this is not a problem, because you're not bound to physical principles, you just want the best possible state, and you don't care whether between today and yesterday there's a bit of a disconnect because you adjusted the model. If you're not interested in that, or that's not important to you, you have much more options like filtering, ensemble Kalman filter, optical interpolation. This probably rings a bell for person 1 or 2 here, the audience. Then you can go and the cool thing about these methods is normally that you can perturbing the model states or model other aspects of a model, assuming that there's a spatial correlation between those modeling errors or the input errors or whatever errors. And if you assume the spatial correlation, you can basically use this generic solution to interpolate data to locations where you don't have that. Because if you know, okay, you have a problem here and you have a problem here, then you can, in this correlation, you can also assume that probably there's also the problem in between. And that's generically available in these methods. However, the problem here is that adjusting the model states can require some very arbitrary decisions. Let's say you need to add some snow because you know, the observations say, hey, there's more snow, and you need to tell the model, okay, add snow. So what do? Do you add new snow? Do you add old snow? What is the density of the snow you have to add? No idea. Nobody will tell you, and the solution is not available here. So you, as the person to implement all that, need to take a decision and say, okay, I decide if I need to add a meter of snow, it's probably new snow, and it has a density of 120 kg per cubic meter. But it can also be something entirely different. So yeah, it's basically a lot of choices that have to be made, and that makes this approach a bit arbitrary. You may or may not care about that. And yes, I'm close to running away. So here is a slide summarizing what I think about those products. You will have that slide. I will probably not read through all of that, but see that basically what I just discussed is somewhat summarized here. And one case that I like to present here just quickly is where you basically combine those different procedures. Here's an instance of a model that was unaware of wet snow map information that I highlighted as something that's interesting from a data assimilation procedure. And after acknowledging this data, you were able to not only improve wet snow bias, so basically that was off-centered, and now it has moved to the center. At the same time, you were also able to improve some snowline issues, combining wet snow information with snow cover fraction information with snow station data. So that's the assimilation of three things at the same time: top row, second row, and third row. So a combination of those three first rows where you can see quite significant model improvements. Okay, yeah, this is where I said I probably don't have the time to do this. I'm exactly at that slide. So just believe we have a great model. That's it, in Switzerland. Thank you. I do believe that those slides will be made available for you. And if you have any questions after I run away, just approach me by email. Thank you so much for being here, and maybe sooner or later we have some interaction. Okay, goodbye everyone.
Yes.
Should I copy it or should I leave it on the stick and open from there?
You can just do it from there, I guess. Yeah.
Yeah, maybe that we have it. I also copy it. Okay.
Okay. Yeah. Okay. Perfect. So we are coming to an end of our training course. So I will just summarize a little bit the week, and then we'll distribute these certificates that I hope you will put in the wall in your living room or over your bed or something. So we are a bit in advance, so hopefully we will, you will be able to leave this course before 2 o'clock. I have just a few slides to show to you. So just to remind you what we did during the week. I think you went through a lot of theoretical principles, processing algorithms, products, tools, methods, and also you saw something about using these products now, for example, in the last presentation of Tobias, how they can be used in the models. So I hope you learned quite a lot about all this, and I also hope that that we were successful in this other very important objective, which is the networking. I just wanted to thank again, particularly Magdalena, in particular also Irene, who really been the people who worked the most from the beginning of this preparation. And then Irmgard, who came in a bit later and has worked really a lot during the last months. thanks again to Thomas Geist, who was very supportive and also offered some funds for our field trip. And thanks a lot to Thomas and to Helmut for all the preparation and the work that you did, and also the teaching you did here, and helping also with probably you had you, Thomas, maybe had this good idea about where we could go on the field trip to the glacier. So thanks very much to you. Thanks again to Irmar and Imgard. Let us make an applause for them. Thanks also to all the lectors. I think we had really top experts to give you some lectures and do practical exercises. I think they had different styles, and some of you might have liked some style, liked other styles. I hope you enjoyed the lectures over everyone. So thanks a lot to the teachers. I got some results from the questionnaires that we asked you to fill in. I think we had 39 by this morning when we downloaded the results. So it looks like generally that you were rather happy about the organization of the course. You see, so after 39 we had like 37 who gave very good or excellent for the organization of the course. The level of the course was also considered to be pretty appropriate, and we also had the same for the level of the course and also for the content of the exercises. So it seems that you were rather satisfied if you were honest when you filled in the questionnaire, and I trust you were that. We had although I said, okay, the level and duration, people are happy, but we heard some comments that it could be better to shorten the days and make the Friday longer. So we take that with us. And for the exercises, some of you said that it would be better to have more time for the exercises. And it's not the first time we hear that. Maybe we have not been good enough to move towards that. But it was a bit like during the preparation we had this nice idea of the field trip, and the field trip took more time than we usually do for the field trips in this course. So of course then it took away a bit more time that we could have put into the exercises. For the level, yes, at some point it was quite hard, but necessary. I heard also that several said that they had learned about things that they never looked into before. Of course, some of you had experience from SAR, some from optical, and of course then, so depending on that, you will learn quite some new things. And of course, between snow and glaciers, most of you were not experts in both, so I hope that you learned a lot of new things also, and I hope there were some useful really things about also the things that you're the most interested in. Was there something else? Yes, most of you were very happy about the field trip that we also saw, yeah. So that was good to hear. A nice image from the field trip. I think we were discussing with Thomas, and Thomas told me in 5 years' time, the only thing people will remember from the training course is the field trip. He's probably right. But I hope that at least in 5 weeks' time, you will still remember some lectures and practicals. The lightning talks, most of you liked it. It's not the first time we did it. I think it was the second or third time maybe we did it. We have modified it a little, and we think it's a nice way to really learn about all you're doing, and And also this aspect that you can find who is doing what, so maybe you can identify some person that works on something that really is of interest for you. So I think that was very nice. Some suggestion was to have some time for questions and feedback, so maybe then we would need some more time for it. And to organize earlier during the week, and that it was our plan to do it on Tuesday. I don't remember why we had to move it, but of course it's better to do it in the beginning of the week so that you can have more time to discuss with those who work on interesting things for you. Yes, so all the materials, so both PDFs of the PowerPoints, the data for the exercises, the guidance documents for the exercises, and videos of lectures will be made available on the website for the conference on the EU for Society. Also, there will be on our website euforsociety.isa.int, and there will be a link from the website of this training course. And we will send out an email to you when it's there. It will probably take a little bit of time because we need to edit a bit the videos, etc. So then I will just make some publicity for a conference that the University of Innsbruck will do next year. So you're working already on this one, yeah? So International Mountain Conference in September next year. I think there is a call out now for a proposal for the sessions, right? And then there will later be a call for abstracts for taking part in the conference. So you can be able to come back to Innsbruck again next year if you want. I think if you enjoyed Innsbruck as much as me, you will probably try this. Maybe I should try to send in an abstract as well. And then we in ISA, we will also have an event in Austria next year, which is our Living Planet Symposium. This is our biggest event in ISA in general. So we do it every 3 years. And last time was in Bonn in 2022, and I think we had more than 5,000 participants. So maybe it's the biggest Earth observation conference in the world. I'm not completely sure, but it's really dedicated to Earth observation. So it's a big event, and there will be several sessions related to snow and glaciers. And I think the call for abstracts will be out maybe in November. I'm not completely sure. So watch out for that. We hope that you will all come to Vienna, because it's really a nice place to see everything that is going on in Earth's observation, both in Europe and worldwide. So with this, I will just thank you, participants, for your contribution to the success of the course, because for me, I consider it a success. I hope you too. It was very nice to see how engaged you were, both during lectures, exercises. Seemed to have very interesting discussion during the breaks, during the field visits, etc. And it was really a very nice group to be around for this week. So thanks a lot to all of you, and then hope to see you again soon, as I said, in Vienna in end of June next year. Thank you very much. And have a nice trip back.
So I will say the name, and then you come out and
Yep.
ask me.
Sorry, I almost forgot that. Sorry.
You wanted to leave.
Yeah, we have this certificate.
Yeah. I hope to spell the names right. It will not be easy every time. So Vanessa, schreib mir nieder. Jacqueline Baumgartner. Baumgart. Sorry. I need my glasses. Vanessa. She's already gone. Vanessa Streifeneder. Jacqueline Bannwort. Arbeit. Claire Webster. Blanca Barbagallo. Lily Beaver. Moon Tavern. Yevan Wang. Elena Anastasova. Melina Friesenbichler.
Oh, sorry.
Jakob Lorenz, Jakob Hafner, sorry. It was another. Iris Hansche. Emma Hauglin. Kasimir Herold. Maria Heinrich. Kasimir first. Andri Gunnarsson. Maje Evans. Okay. This is a very, yeah, I think it's you, yeah. Edward Holt. Julia Kaltenborn. Marti Maccelloni, Marco Mazzolini. Hanna Müller.
Thanks so much for organizing. This was really nice on our side.
Joy Oslo still.
Jasper Heuer.
Thanks so much.
Oh, Shuyin Yia. Ja. Andres Rebetto, sorry. Caroline Watts Michael. You're welcome. Anna Marangunik. Anna Maria Marangunik. Heitan Alois. Heitam. Sorry, very Unusual name. Celia Baumhor. Lukas Boyekens. Jamie Marina Wistjup. Ines Dussayer. Mostafa Busba. Harry Davis. Elena Navieva, no, the other Elena. Ragnar Brastersen. Andrea Securo. Andrea Securo?
He's not here.
He's not here. Okay. Ephraim Sebetta. Jérôme Pigion. Jérôme Pigion. Okay. Anto Reira. Jérôme.
Pardon?
J'espère que c'était bien.
Ouais, c'était très bien, merci.
Ah, sorry?
Thanks a lot again for the present. Francesco Salvaterra. Andreas Colamiero. Kirsten Schulze. Patrick Schmidt. Katharina Scheidt. Tanja Rahim. And last but not least, I hope we didn't forget anybody, Alexandra Osika. So I hope everyone got his certificate. Have a good trip home.